Before the conservation of momentum was discovered, no one knew what exactly went on within collisions.
Why is it that when a moving object comes in contact with an object at rest and sticks to it, the system will move off at a slower velocity?
Why is it that when a pool ball is struck and comes in contact with another ball, the ball that started off with some velocity will come to a rest, but the ball that it came in contact with will move on with the velocity of the other ball?
All of these questions were beginning to be answered with the work of René Descartes.
The modern definition of momentum is mass times velocity. Momentum is a vector quantity having both magnitude and direction. The history of momentum goes back to the 16th century. René Descartes, Sir Isaac Newton, and I, Christian Huygens, contributed to momentum in the law of conservation of momentum.
I, René Descartes, am a French scientist, mathematician, and philosopher. I published a definition of momentum in 1644. Importantly, I stated that a quality of motion of an object was its mass multiplied by its velocity. My quality of motion was a scalar quantity. I was also the first to examine collisions between bodies. I analyzed the change of motion of bodies produced as a result of collisions. I stated that the motion lost by one body is gained by another. The overall amount of motion in the system remains the same, but I explained only very few types of collisions in the natural world.
I am a Dutch mathematician, astronomer, and physicist. I accepted Descartes' statements for both bodies approaching each other with equal velocities. However, I generalized the principles to all collisions between bodies of equal mass. When a moving body strikes a stationary body of equal mass, the moving body comes to a stop. The stationary body begins moving with the same velocity as the other body. Think about pool. If a ball strikes another ball, the first ball will stop, and the second ball will travel at the velocity of the first.
Huygens also addressed conservation of momentum during a collision of bodies of unequal mass. He stated that the total quantity of motion should be the same before and after a collision. This is the first statement of the law of conservation of momentum. Bodies can either move in the same direction or in the opposite directions. When both bodies are moving in the same direction, the total quantity of motion is the addition of the two quantities. When the bodies move in opposite directions, the total quantity of motion is calculated by subtracting one body's motion from the other body's motion.
Sir Isaac Newton was influenced by both Descartes and I. Newton stated the law of conservation of momentum in even more general terms. In 1687, he published his 3 laws of motion. The third law states that the forces of action and reaction between the two bodies are equal, opposite, and collinear. Within less than 50 years, momentum proceeds to a mathematical equation and the law of conservation. Momentum before equals momentum after.
There are 3 different types of collisions, all in which momentum is conserved. First, you have an elastic collision. In a perfectly elastic collision, momentum will be conserved, and kinetic energy of the total system will be conserved. Here are some examples of elastic collisions.
Here's an example of an elastic collision. This is plate 1 and this is plate 2. As you will see, plate 1 will stay roughly in the same location as plate 2 before the collision, and plate 2 moved at roughly the same velocity as plate 1 before the collision.
Some more types of elastic collisions are atomic or nuclear particles with similar charges and magnets with similar poles facing each other.
The next type of collision is an inelastic collision. Unlike an elastic collision, kinetic energy is not conserved due to the action of internal friction, but momentum is still conserved. In such a collision, kinetic energy is lost by bonding the two bodies together. This bonding energy usually results in a maximum kinetic energy loss of the system. Here's an example of an inelastic collision.
This is an example of an inelastic collision because one person starts at rest and one person has a velocity, and in the end both bodies stick together. The last type of collision is an explosion. All objects before an explosion initially start at rest. After and during the explosion, the objects fly away in different directions and in different speeds. Momentum is always conserved. In this case, the initial momentum for everything is 0. Knowing this, the final momentum must also be 0.
In the exploding water bottle demonstration, total system momentum is conserved. The system consists of 2 objects, a water bottle and a cap. Before the explosion, the total momentum of the system is 0, since the water bottle and the cap located on it are both at rest.
After the explosion, the total momentum of the system must still be 0. If the cap acquires 50 units of forward momentum, then the bottle acquires 50 units of backwards momentum. The vector sum of the individual momenta of the 2 objects is 0. Total system momentum is conserved.
Give me those physics answers.
No, that's cheating.
You're gonna feel the explosion now.
As you can see, in this collision, momentum is also conserved because the system starts with 0 total momentum before the collision, since it is at rest, and 0 total momentum after the collision is also 0 because the sum of the momentum of the gun and the bullet will add up to 0.
In conclusion, there are 3 different types of collision: elastic, inelastic, and explosion. In an elastic collision, kinetic energy and momentum are conserved. In an inelastic collision, the colliding objects stick together and become one. It involves the greatest loss of kinetic energy, and keep in mind that if it loses Ke, the energy will appear as heat or sound. In an explosion, the total momentum is conserved because it starts off with 0 and ends up with 0 after the collision.
Did the discovery of momentum and the conservation of momentum lead to any other discoveries?
Yes. After Descartes found out about the general principle of momentum, it turns out the conservation of momentum can be deduced from Newton's laws.
I don't understand though. How does it relate to Newton's laws?
You don't understand? Well, Newton's laws in principle fully describe all collision type phenomenon and therefore must contain momentum conservation.
Oh, I get it. So to understand how this comes out, we must first consider Newton's second law relating the acceleration of a mass to the external force acting on it.
So basically you're saying F equals ma.
Yeah.
Newton actually continued Descartes' work and produced the 3 laws of motion after Descartes found out about momentum. And since acceleration is just the rate of change of velocity, Newton's second law can be written as force equals mass times the rate of change of velocity.
That makes more sense.
It also led to the discovery of angular momentum, because without knowing there was any linear momentum, we would have never known about angular momentum.
What the heck is angular momentum?
It's quite simple, my friend. Momentum is the quantity of rotation of a body, which is the product of its momentum of inertia and its angular velocity, L equals IW.
Wow, Descartes and Huygens' discovery of momentum led to a lot of other huge discoveries in science.